All right, so we're live now, or not live, but recording now, I should say. All right, so I encourage you guys to work through all these problems. Again, these are not real exam problems. These are ones that I made up, but they do follow the sequence and the topics that you will have on the final exam. So, you can look at this and see, okay, there's one question on this topic. That means there's going to be one question on that topic likely on the final exam. So it's all the questions on the final exam are divided up by topic. Of course, there's a lot of individual problems within there that you could get, so this may not be perfectly representative, but at least from a topical standpoint, it will be. And what you'll find as we go through these is that the questions are divided up roughly equally between the different chapters in the course. So we have 9 chapters, we have 34 questions, so you guys can do the math and find out there's roughly 3 or 4 questions per chapter. Now there's going to be some questions that maybe bridge the gap between 2 different topics, of course, and then it's probably a little bit heavily weighted towards the most recent stuff because there is, again, part of Chapter 9 that we haven't tested you on at all yet, so maybe a little bit heavily weighted towards that, but in general, a pretty equal distribution of all the topics that we've covered. And so when I talk to students about the final exam, many of you have asked about it already, it's not typically, the averages are pretty similar to the second and third midterm, so it's not necessarily harder from that regard in terms of the scores. It's actually, in some cases, the average is a little bit higher, so it's not too bad. The difficulty in the final exam is I don't think we pick the most difficult questions to give you, but it's all topics. You have to make sure that you can cover everything. So the individual questions that we do are, I think in most cases, pretty straightforward. You guys sometimes disagree with me on that, but at any rate, I think we mostly picked straightforward questions, pretty predictable questions for the different topics that we cover, but you have to make sure that you're comprehensive in covering everything. So we just had an exam on a third of the material, so you guys should be, for the most part, pretty well set up on that, but you have to definitely go back to the old stuff we haven't seen in a while and make sure you know how to do it. And that's what we're going to start with today, is a lot of the most, really take a trip down memory lane back to the beginnings of the course. Okay, as usual for an exam review, you're welcome to stop me anytime with additional questions you have, either on the particular problem that I'm doing or just related to that topic in a more general sense. So please speak up if you have anything you want me to stop and clarify. So this first problem deals with mass ratios, which was sort of an offshoot of the mass laws that we learned at the very beginning. So if we have a compound with iron and sulfur in it that has a mass ratio of 1.16 to 1, we want to know how many grams of sulfur are contained in 3.5 grams of this sample. So this was like way back before we knew anything about moles, mole ratios, stoichiometry, any of that stuff, where we just use mass ratios to classify different compounds and to talk about the masses of each element in that compound. So if we have a 1.16 to 1 ratio of iron to sulfur in this compound, what that means is that if we want to do it in terms of grams, that means we have 1.16 grams of iron in the compound, 1 gram of sulfur, and that would be per 2.16 grams of whatever the iron sulfide compound is, which we don't know the exact formula of. So we can use either of these as ratios, or any of these combinations as a ratio. 1.16 grams of iron per gram of sulfur, or vice versa. 1.16 grams of iron per 2.16 grams of compound. 1 gram of sulfur per 2.16 grams of compound. Any of these combinations work as a mass ratio to describe that compound. And so that's how we're going to then approach this question here. We want to know how many grams of sulfur are in 3.5 grams of the compound. So we're going to solve for grams of sulfur, given that we have 3.50 grams of the compound, which again we don't know the exact formula of, so we can't use mole ratios or anything very easily to do this. And then we want to get to grams of sulfur, and we want grams of the compound to cancel out. And from the mass ratio, we know that there's 1 gram of sulfur for every 2.16 grams of the compound. All right, what we're told is that there's 1 gram of sulfur for every 1.16 grams of iron. The sum of those two is the mass of the compound that would form, and so this ratio is also valid. So that cancels out. We just multiply that, and we get 1.62 grams. All right. So hopefully, in light of some of the more complex problems we've done more recently, this now seems fairly simple. But again, a lot of times people, they forget the basics as they go through the more complex stuff. So this one, again, we're just using mass ratios only, nothing with moles, nothing with molar mass, to figure out something about this compound. So any questions on this? All right, so I think that one was a really good way to start. Another topic which certainly will be covered in the final exam is subatomic particles. So number of protons, neutrons, electrons, and so on that are found in a particular element on the periodic table given the atomic symbol. All right, so as a review of what this involves, we have atomic symbols written in this way, where we have the symbol for the element given as a series of letters, 1 or 2 letters. We have Z on the bottom and A on the top are the 2 numbers that are often attached to that. All right, so Z here, which is the bottom number, is the atomic number. Which is the number of protons in the nucleus of that element. So remember, it's the number of protons in the nucleus that defines a certain element, and so that number tells you what element it is. Remember that the atomic number is not always given to us in the symbol because it again corresponds to that specific element only. So if we don't have the atomic number given to us, we can get it off the periodic table. All right, so in this case, if we didn't give you the atomic number of 42 here for MO, you would just find that on the periodic table. And we find that molybdenum and MO is over here, number 42. So the number above the element symbol is also the atomic number. So if we don't give it to you, you can get it off the periodic table, no problem. Okay? So that's not always given, but you can get it from the periodic table. And then this other number A, this is called the mass number. And this has to be given to you because it's different for each isotope. All right, so it's going to be the number of protons plus the number of neutrons is the mass number A. And recall that for most elements, you're going to have different isotopes that have different mass numbers. So this is one specific isotope for MO molybdenum, but likely there are others that would have different numbers of neutrons and thus different mass numbers that are all still the same element. So those are called isotopes as a reminder of that topic. So that's what the mass number refers to. So if we want to be able to determine then the number of electrons, the last thing is going to be number of electrons is just going to be equal to the number of protons if it's a neutral element. Okay? If it's an ion, you would have to adjust that by either adding or subtracting electrons based on the charge. The charge will be given up here in the top right. There's nothing there, so we know that this is neutral, meaning it has equal numbers of protons and electrons. So looking at this symbol here, we have Z is equal to 42, as we already said, which is the number of protons. And because it's a neutral element, that's also the number of electrons. So it's going to have 42 each for protons and electrons. And then to find the number of neutrons, the mass number is 96, which is 42 protons plus the number of neutrons. So the number of neutrons, abbreviated as N0, is going to be 96 minus 42, which is 54. All right, so typically the number of neutrons we get by subtracting the atomic number of protons from the mass number, which is the sum of those. So we have 54 of those, 42 protons and neutrons. Correct answer is choice A for this one. All right, any questions on subatomic particles? All right, so hopefully this is all coming back. All right, the next question on this deals with properties of electromagnetic radiation. Frequency, wavelength, energy, all those things that are how they're related to each other. And so we want to know, what is the frequency and energy of a blue photon with 485 nanometer wavelength? All right, so for anything dealing with photons, again, dealing with energies, wavelengths, and so on, there's 2 equations we need to know, which is that the product of the wavelength and the frequency equals the speed of light, c. So lambda is wavelength, nu is frequency. Here we're given the wavelengths, that's our given information in this. And then if we want to know the energy of a photon is equal to another constant, h, Planck's constant, times the frequency. And then combining these 2 equations, we can also write this as h times c over lambda. So solving for lambda in this equation is solving for nu in this equation is c over lambda. We replace that, and we have 2 forms of the same equation. So that's what we're going to want to use if we do anything involving wavelength, frequency, energy of photons. For these equations, though, the fundamental constants, c is in meters per second, h is also in SI units of joule seconds, so we always have to make sure that our wavelength is in meters if we're going to use this. So for this problem, we need to convert the wavelength 485 nanometers into meters to be able to use these equations. So remember that nano is 10 to the minus 9, so 1 meter has 10 to the 9th nanometers if you prefer to use positive exponents. So when we divide that, we get 4.85 times 10 to the minus 7 meters is our wavelength. And that number we can then put into these equations. So if we're going to solve first for the frequency, using this first equation here, frequency nu is equal to c divided by lambda. C is the speed of light. It's on our periodic table, so we don't have to memorize it. It's 3 times 10 to the 8th meters per second. And we're going to divide that by this wavelength, 4.85 times 10 to the minus 7 meters. And so we get 6.18 times 10 to the 14 hertz. All right. Often in these problems, we would also potentially ask you to take the log of this number and report that, so make sure you're familiar with that function on your calculator. And then the next one is the energy of the photon. So that's the frequency. We want to find the energy of the photon as well. Energy, as we said, is equal to h nu. So we can either do hc over lambda and put this wavelength back in, or we could just do h times that number since we already calculated it. It works both ways. So h times the frequency is going to be, h is 6.626 times 10 to the minus 34. Again, that's on your periodic table, so it's there for you if you need it. And then we're going to multiply that by the frequency we just calculated, 6.18, 8 times 10 to the 14 hertz. And we get 4.09 times 10 to the minus 19 joules. All right, so the correct answer would again be choice A here for both frequency nu and energy E for the photon. All right, so any questions on properties of electromagnetic radiation? Another thing you're going to want to be able to do that's somewhat related to this is, I'll cover this real quick because there are a few problems on it, sort of ranking the different types of electromagnetic radiation in terms of their frequency or wavelength or energy, okay? So we have to remember that in terms of increasing energy, we would have the lowest energy is going to be the radio waves, then microwaves, then infrared, then you have visible, ultraviolet, which is UV, X-ray, and gamma ray. All right, so it's not that likely that you get a question like this in your exam because there's only a few in the question bank, so it depends on luck of the draw, really. But also make sure that you can at least qualitatively rank them in terms of their energy. So this is increasing energy or frequency as well, because those two are directly correlated. Would increase left to right. The wavelength increases in the opposite direction, left to right to left. All right, so that's how they sort of, I shouldn't do that because it's going to confuse people. So that's the increase in energy and frequency. The increase in wavelength would be in the opposite direction. So remember that visible is right in the middle. You have 3 below visible, 3 above visible. And make sure you can put those in order if you need to. All right, so any other questions on electromagnetic radiation? All right, so we're now moving on to some questions that deal with more like quantum theory, electron configurations, and stuff of that sort. And so this first one here wants to know how many electrons in a hydrogen atom can have n equals 5, and how many of these can be in a 5f subshell. Enter the two numbers without units separated by a comma and a space, and so on. Okay, so this is dealing with quantum numbers, which again are the mostly integer parameters that deal with solutions to the Schrodinger equation, and they allow us to characterize electrons and atoms that are arranged in different orbitals. So we have 4 quantum numbers. We have n, l, m sub l, and m sub s. And the two that we need to consider for this one are n and l. These are the subshell designations, because that's what we're dealing with here, are shells and subshells. So when we talk about n and l being the first two, that's going to determine how many electrons are in a shell or a subshell. So here we want to find the maximum number of electrons that can have n equals 5, and then how many of these are in the 5f subshell. So we're talking about maximum number of electrons. There are some helpful relationships that we should remember to be able to do this. We don't have to necessarily count everything out. So a shell is defined by quantum number n, And if we want to know how many electrons can go into a given shell in an atom with a given value of n, it's going to be 2n squared. Okay? So that's going to be one that we want to remember to help us for some of these, is that there are maximum of 2n squared electrons in a given shell. And then the maximum number of electrons in a subshell, as we'll see, only depends on the value of L. So a subshell is defined as n and L together. But the number of electrons that goes into that subshell only depends on L. So it's going to be 2 times the quantity 2L plus 1. Okay? So those are the two relationships that allow us to determine the maximum number of electrons that's going to go into a shell or subshell. That doesn't mean that they always have that number. That's the most that you could put in any atom on the periodic table. All right, so the first one, if we have n equals 5, which is the shell number we're considering, the maximum number of electrons is going to be 2 times n squared, so 2 times 5 squared, which is 50. So that means at most we can put 50 electrons into the n equals 5 shell, and then how many of those can go into the 5f subshell? So for this we need to think about the value of L. So for 5f, n is still 5, but then the value of L is going to be what? So remember that these letters in a subshell designation represent the values of L that we have. So you have S, P, D, and F are the ones that we encounter most common, and that gives us values of 0, 1, 2, or 3 for the L. So an F subshell has L equals 3, so that's the value of L that we're going to want to use for this one. All right? So the maximum number of electrons in 5f is going to be 2 times the quantity 2 times 3 plus 1, 2 times 2L plus 1, which is 2 times 7, or 14. All right, so the correct answer for this one would be 50, 14, separating the two numbers as we instructed you to do. All right, so out of those 50 electrons that could go into the n equals 5 shell, a maximum of 14 could be in the 5f subshell. And there would be 14 electrons maximum in any of the f subshells. It doesn't matter if it's n equals 4, n equals 5, n equals 6. The number of electrons in a subshell is only determined by the value of L, not by the value of n. Okay, any questions on this? All right. All right, and there are also several questions like this that deal with electron configurations, either giving the electron configuration, or if we give the electron configuration, telling us what element it is, working again in both directions, as we said you'll have to be able to do for these types of tests. So we want to know the atomic symbol and the number of unpaired electrons for the element that has the following electron configuration: krypton 5s2 4d6. So remember, when we're doing electron configurations, the location on the periodic table tells us which of the subshells we're filling. And very often when we do this, we use the core electrons from the noble gas as sort of a shortcut. All right? So if our configuration is Kr krypton and then 5s2 4d6, we have a core electrons that are krypton, so those are the 36 core electrons that we have. And then we're going to go and find out where the valence electrons take us. So krypton, the next row of the periodic table is the 5s block. It's 1, 2, 3, 4, 5, and this first two columns are s. So that's 5s2. And then we said it's 4d6, so we're starting with the 4d here. We have 4d 1, 2, 3, 4, 5, 6. So the element that we'd identify as ruthenium, Ru, is the symbol. And so that's going to be the element that we have there. So the element symbol is Ru. There's actually an easier way to do this. Instead of just going to the periodic table like I did, let's just do a little bit of math. So the total number of electrons in this element, we have 36 from our noble gas core kryptons, that's atomic number 36. We have 2 from the 5s2. We have 6 from the 4d6. So 32, 6 plus 8 is 44. So that means this will have atomic number 44, 44 electrons in it. So without even necessarily thinking about the actual configuration, atomic number 44 is ruthenium. So if it has 44 electrons, so if we give you the electron configuration and you're asked to find the element, I think the easiest way to do it is just figure out how many total electrons that is, and then find that number on the periodic table. So don't necessarily worry about thinking about all the different subshells and things of that sort. So that's how we can identify that the element is ruthenium, Ru. But then we need to think about how many unpaired electrons there are, which is the second part of the question. So to figure out the number of unpaired electrons, we only need to consider the partially filled subshells. So krypton, which is the noble gas core, those are all filled, obviously. 5s2 is a filled 5s subshell, so that's not going to have any unpaired electrons in it. But 4d6 is a partially filled 4d subshell because d subshells can hold up to 10 electrons. Remember that the d block of the periodic table has 10 elements across, so there's 10 possible electrons that can go in there. So for the partially filled subshells, we need to draw them out. So if you have a 4d subshell, L is equal to 2, so 2L plus 1 equals 5. So you have 5 orbitals in any 5d subshell, or any 4d subshell, or any d subshell is going to have 5 orbitals. So in 4d we have 1, 2, 3, 4, 5 orbitals, and we're going to fill those with 6 electrons as this configuration tells us. So we're going to fill them one at a time first. 1, 2, 3, 4, 5. That's how we follow Hund's rule, and then the 6th one has to pair up. So in terms of number of unpaired electrons, it's going to be 4. So we have 4 electrons that are unpaired in this configuration. All right. So the correct answer for this one, the element would be ruthenium, and the number of unpaired electrons is 4, and that's going to be the answer we would put in. Okay? So whenever you need to think about number of unpaired electrons, you do need to draw out at least the partial orbital configuration for the partially filled subshells. So if this was 4d, there'd be 5 of those orbitals. 6 electrons are going to arrange this way to maximize the number of unpaired electrons, and that leaves us with 4 that are unpaired. All right, so any questions on those concepts? Electron configurations, or any of the rules that we have for building configurations out? All right, last one we'll go through today. I guess you guys probably won't be too upset if we finish up early. So which of the following is a valid set of quantum numbers for an F electron? So we're back to the F subshell again. So this one requires us to think a little bit more completely about the quantum numbers that we have. Which again, there's 4 of them. There's going to be N, L, M sub L, and M sub S. And it's also helpful to sometimes think about what these quantum numbers mean for us. So, we have these 4 different quantum numbers that are going to define each electron in an atom. The first 3 define the orbital that the electron is in. The last one is a property of the electron itself. So think about what these mean, which isn't really important for this question, but is helpful for us to review. The first quantum number n, which we said is the shell number, tells us the size and energy of the orbital. So larger values of n refer to shells that are on average farther away from the nucleus and also that are higher in energy. The L quantum number is what tells us the shape of the orbital. So remember, the L quantum number is associated with those letters S, P, D, and F. S orbitals being spherical, P orbitals being sort of figure 8 shaped, and then D orbitals mostly having 4-leaf clover shapes, and then F orbitals being way more complicated than that, so not to worry about. But again, L tells us the shape, and also it contributes to the energy as well, or anything that has more than one electron. So in multi-electron atoms, which is everything but hydrogen, the value of L is also an important, I'll eventually write that word correctly. There we go. So it also determines the energy of the orbital to some extent when you have multi-electron atoms. So N and L together determine the energy of an orbital for a multi-electron. And then M sub L tells us the orientation of the orbital. And M sub S is just a property of the electron. It's the spin quantum number, which is either plus 1/2 or minus 1/2, and really has no bearing on anything related to energy. All right, so those are the 4 quantum numbers, a little bit about what they mean. And the rules that we have then are going to be, to summarize the rules for quantum numbers, n is going to be a positive integer, 1, 2, 3, and so on. Those are the possible values of n that we have. L is equal to, the first one is 0, and then it also has integer values up to n minus 1. So depending on what the value of n is, that's going to dictate which values of L you can have paired with that. And then M sub L is determined by the value of L that you have, which is minus L, including 0 and all the way to positive L. So again, integer values spaced by 1, but that includes negative and positive in this case for M sub L. And then as we said, M sub S is just plus 1/2, minus 1/2. Those are the restrictions on that. So to answer this question, we need to think about the relationships between these 3 quantum numbers and which of these sets is going to be valid. We notice that all of them have either plus 1/2, actually all of them have plus 1/2 for the 4th quantum number, so that one's going to be fine. So we need to think about which of these has a correct grouping of the first 3 quantum numbers. So if we're talking about an F electron here, as we reviewed a little bit earlier, that tells us the value of L. So L can be 0, 1, 2, 3, and so on, which corresponds with the letter S, P, D, and F. So if we have an F electron, that means L must be 3. L is typically the second quantum number given. So if L equals 3, we can find the ones that don't have L equals 3 and cross them out. So choice B has the wrong L, and also choice E. That's 2, that's 4. But choices A, C, and D all have the second number equal to 3, so all of those at this point could be valid answers. So to think about the rest of this, we need to think about if L equals 3, what's the smallest value of n that we can have? Or we're working backwards with this rule here. So L goes from 0, 1, 2 to n minus 1. So if L equals 3, what's the smallest value of n? 4. So it has to be at least 4 to have an L equals 3 subshell. So that means n has to be greater than or equal to 4 for this. So that allows us to cross out choice A because we can't have n equals 3 and L equals 3. If n equals 3, the biggest value of L would be 2. And then finally, to distinguish between C and D, we need to think about m sub L. So the allowed values for m sub L is going to be, again, minus L to plus L. So it's going to go minus 3, minus 2, minus 1, 0, 1, 2, and 3. Those are the 7 allowed values of m sub L for an L equals 3 subshell. And that one has the wrong m sub L value. So the only one where everything follows all the rules is choice C. N equals 4, which means L could be 3. If L equals 3, minus 3 is a valid number for m sub L. And then m sub S plus 1/2 is no problem. All right, so any questions on quantum numbers or the rules that relate them to each other? All right, so that gives us a flavor of some of the early stuff. We will continue on Friday with the next part of the review, which will take us through most of the rest of exams 1 and 2. And I'll see hopefully most of you then.